What's going on, everybody? Back for another video. This one's on partial derivatives. Alright, so let's get started. We've got a definition here. It says if f is a function of two variables, its partial derivatives are the functions f's x and fy defined by fx of xy is equal to the limit as h goes to 0 of f of x plus h y minus f of xy over h, and fy xy is equal to the limit as h goes to 0 of f of x y plus h minus f of xy over h. All right, so that's finding the partial derivative using the limit. We're not going to work any problems like that, but there you go. That's the definition. And then we have notations for partial derivatives. So these are the different ways that you can write it. You can write it with this subscript x and the xy, or you can leave the xy off. This is the partial of f with respect to x, the partial of f of xy with respect to x, or partial z with respect to x, and then you've got f1, d1f, d sub x, f. Now, these last two, or these last three right here, you won't see those much. Mainly we'll write it like this, and this, or this. That's the ones that we'll use mainly. So these are this is the notation for the partial of f with respect to x. And then down here you can see it's similar. This is the partial of f with respect to y, or the partial of z with respect to x, partial of z with respect to y. You can see we have the function z equals f of xy. And for this notation over here, you can see it's f2, and that should be d2, not d1. All right, so finding partial derivatives is easy, okay? If you know how to take the derivative already, which you learned in Calc 1, you should be able to do this. This right here is what you've got to know. You just got to remember this. So to find fx, the partial of f with respect to x, you just treat y like a number and then differentiate with respect to x, just like you always do. You just when you see y, you say, well, that's a number. And then the same thing to find the partial of f with respect to y, you treat x as a number, as a constant. And then you differentiate with respect to y. All right? So let's do some examples. So if we have f of xy equals this, find the partial of f with respect to x and evaluate it at the point 2, 1, and find the partial of f with respect to y and evaluate it at the point 2, 1. All right, so let's go ahead and do it. So we've got fx xy. So we're taking the partial of f with respect to x. So the derivative of x cubed is 3x squared. The derivative of this is what? Plus 2xy cubed. Okay, so look, the 2 comes down, subtract 1 from the exponent. Y cubed is a number. Okay? It's just multiplied to that. And then what's the derivative of this? Well, that's 0. Because see, the only variable here is a y. And we're treating y as a number, okay? And then we can evaluate this at the point 2, 1. So that's going to be 3 times 2 squared plus 2 times 2 times 1 cubed. And that is going to give us 16. All right? And then if we take the partial with respect to y, so we're treating x as a number. So the derivative of x cubed is 0. And then this one, the 3 comes down. And subtract 1 from the exponent. It's just a simple power rule. And then minus 4y. Derivative of this is 4y. And so then we've got this partial evaluated at 2, 1. So that's going to be 3 times 2 squared times 1 squared minus 4 times 1 is 8. And there's your answer. You see how easy that is? Nothing to it. All right, let's look at another one. So we've got f of xy is sine of x over 1 plus y, and we want to calculate this. All right, so we've got the partial of f with respect to x. All right, so the derivative of sine is cosine x over 1 plus y times the derivative of what you're taking the sine of. So what's the derivative of this? So that's just 1 over 1 plus y. And there's your answer. All right, so let's look at this. So x over y plus, let me write it in a different color. This isn't part of working the problem. This is just something a little extra to show you. All right, so you see this? You can look at this as being 1 over 1 plus y x. You see, this right here is just a number. So let's say we have 5x. What's the derivative of 5x? It's 5. What if you have negative 7x? What's the derivative of negative 7x? Negative 7. So this right here, this 1 over 1 plus y, that's just like this 5 and this negative 7. So what's the derivative of this? Well, it's just 1 over 1 plus y, which we get right there. Okay. All right. Now, let's find the partial of f with respect to y. All right, so derivative of sine is cosine x over 1 plus y times what? Times the derivative of what we're taking the sine of. So here I'm going to need to use the quotient rule. So the quotient rule, derivative of the numerator, which is 0, derivative of x is 0, because remember, x is treated like a constant. So derivative of the numerator times the denominator minus the derivative of the denominator. So the derivative of 1 plus y is just 1. Derivative of 1 is 0. Derivative of y is 1 times the numerator. And this is all over the denominator squared. And so this is going to give us cosine x over 1 plus y times negative x over 1 plus y squared. And let's just clean this up. Let's put the negative out front. So negative cosine x over 1 plus y times x over 1 plus y squared. And there's your answer. And that's it. Okay. That's taking the partial derivatives. You just got to keep in your head that if you're taking the derivative with the partial with respect to x, you treat y like a number. If you're taking the partial with respect to y, you treat x like a number. All right. So let's look at this, interpretations of partial derivatives. All right, so we've got some surface here, and we've got a point here, A, B, C, and we've got this curve C1 and a curve C2. So the partial derivative, so the partial of x, the partial of f with respect to x, and the partial of f with respect to y, evaluated at AB, at the point AB, can be interpreted geometrically as the slopes of the tangent lines at the point ABC. To the traces C1 and C2, remember traces, you learned that earlier, what a trace was, of S in the planes y equal b and x equal a. So you see you have this trace right here, this C1, and this red line here, that's a tangent line to the curve at that point. And then you have C2, okay? So that's this curve C2, and you have your tangent line right here going through that point is tangent to that trace C2, okay? And so that's, it's kind of like when you, in single variable calculus, slope of the tangent line. Okay. All right. So let's look at this example here. It says if f of xy equals 4 minus x squared minus 2y squared, find f(1,1). I didn't write everything. The partial of f with respect to x at the point 1, 1, and the partial of f with respect to y at 1, 1, and interpret these numbers as slopes. All right. So let's find fx xy. Let's find the partial with respect to x. So that's just going to be negative 2x. The derivative of 4 is 0. The derivative of this is negative 2x. And then this is just a constant, so that's 0. And I guess let's just go ahead and find the partial of f with respect to y also while we're here. Okay, that's 0, 0, and then this is going to be negative 4y. And then let's evaluate each of these at the point 1, 1. So that's negative 2 times 1, which is negative 2. And this is negative 4 times 1, which is negative 4. All right. So what do we have here? All right. So this tells us that the slope of tangent line at 1, 1, 1 is negative 2. And this tells us slope of tangent line at 1, 1, 1 is negative 4. Okay. All right. So let's look at this a little bit better. All right. So just to save time in the video, let me make sure I don't have enough room down here. All right. So I guess I'm just going to bring over one at a time. Let me see. Let me move this. Let me move this over here. All right. So I've got a picture drawn of this. So let's take a look at that. All right, so let's bring the figure in for this first part. And I hope I have enough room to get it in there. All right, let's put this. Come on. Okay, right there. All right, so here we have this. Okay, so we have when y is equal to 1. Okay, well, first off, this function here is a paraboloid, and it looks, we'll look at it right here in this xy plane here. So we've got z equals 4 minus x squared minus 2y squared, and when y is equal to 1. Okay, so when y is equal to 1, if we plug 1 in for y, okay, because see, we're at the point 1, 1, or yeah, that's what we're looking at, 1, 1. All right, so if we take y to be 1, that's going to give me 4 minus 2 is 2. So this is going to give me z equals 2 minus x squared. Okay, and that's this curve C1 here. And you can see this red tangent line here, that has a slope of negative 2. Okay, and so that's what you're looking at. That's what you found, this slope of -2. So at that point, 1, 1, 1, well, when y is 1, well, there it is. And notice that this tangent line slopes down in the positive x direction. See, this is your x-axis here, and this is your y, and this is your z. So notice how this tangent line slopes downward in the positive x direction, and we have a slope of -2. Okay? All right, so let's move this one back, and let's look at the other one. Let's see if we can get this back up here. All right, and then let's bring in the drawing I have for this one. I just went ahead and drew these to save time, and I'm not very good at drawing. All right, so now here we have, let's take x to be 1. So if I plug x into here, and I didn't write this. This is z equals 4 minus x squared minus 2y squared. So if we take x to be 1, so that's a 1 there, 4 minus 1 is 3, we would get z is equal to 3 minus 2y squared. And there's your curve C2. And then here's your tangent line to that curve at the point 1, 1, 1, which that has a slope of -4. And notice how this is sloping downward in the positive y direction. All right, so there's finding the slopes and kind of interpreting what they are, and giving you a little picture of it. Okay, and I know my drawings aren't the best, but I think I did a pretty good job on those. All right, so now let's look at this. We've got us a little word problem here. And it says the body mass index, or BMI, of a person is B of MH is equal to M over H squared. Calculate the partial derivatives of B for a young man with M is 64 kilograms and H is 1.68 meters, and interpret them. All right. So let's write our function down. That's M over H squared. Now let's take the partial of B with respect to M. So if you look at this, remember that's the same thing as 1 over H squared times M. Remember the H is our constant. M is our treating it like a variable, treating H like a constant. So this is just 1 over H squared. And now we want to calculate this at the point of 64, 1.68. And if we plug that in, that's 1 over 1.68 squared, which that gives us about 0.35 kilograms per meter squared per kilogram. All right, so that's what we get when we calculate it. All right, so now they want us to interpret this. So this is the rate that the man's BMI increases with respect to his weight when his weight is 64 kilograms and his height stays the same. It's at 1.68 meters. So his weight's going to change, but his height's not. So if his weight increases by a small amount, let's just say 1 kilogram, and his height stays the same, then his BMI will increase by about 0.35. Okay? And then if we take the partial of B with respect to H, all right, so let's look at this. So to take that derivative, let's kind of rewrite this a little bit. Let's write this as, I tell you what, let's write it down here. Let's write this BMH. So I'm taking the derivative with respect to H. So M's going to be a constant. H is my variable. So I'm going to write this as M times H to the -2. I'm going to move it up so I can just use the power rule. So I've got the partial with respect to H is equal to -2mH to the -3, which is -2m over h cubed. And then if I take the partial and evaluate it at 64, 1.68, that's going to give me -2 times 64 over 1.68 cubed. And that gives me an answer of about -27 kilograms per meter squared. Kilograms. I hope I got all that on the screen. I think I did. So this is what they were wanting us to find here. And so, you know, this is similar. This is the rate that the man's BMI increases with respect to his height when his weight is 64 kilograms. And his height's 1.68 meters. So if the man's still growing, if he's still getting taller and his weight doesn't change while his height's increasing, so if his height's increasing by a small amount, say 1 centimeters, then his BMI will decrease by about -27 times 0.01. Well, no, I don't know if I said increase. If I did, that was wrong. So that means his BMI will what? Decrease. We're going to write decrease instead of putting a minus sign, okay, by about 0.27. Because, you know, we said if his height increases by 1 centimeter, so we're putting it back in meters. All right. So that's kind of, you know, that's the idea behind that problem, you know, interpreting the results and the previous problem. So, you know, this is just a little word problem with the BMI. All right. So let's look at this. So it says find the partial of z with respect to x and the partial of z with respect to y if z is defined implicitly as a function of x and y by this equation. So this is going to go back to implicit differentiation. Okay, so this is going to be the partial of z with respect to x. All right, so here, okay, so listen real careful here. All right, so we're differentiating the partial of z with respect to x. So we're treating y as a constant, differentiating with respect to x, and z, we're treating z as a function of x. Okay, you remember when you learned implicit differentiation, just a simple one here, if we wanted to find the derivative with respect to x, that was what? 2x plus 2y dy dx equals 0, right? Since we were differentiating with respect to x, y was a function of x, so it was 2y times the dy dx. This is similar. We're just doing it with the z, and then we'll have to solve. And remember here you had to solve for dy dx. All right, so let's do it. So this is 3x squared plus, that's 0, right? because y is a constant, plus 3z squared partial of z with respect to x, all right, plus, now look at this term here. Here, we have to use the product rule, right? The product rule. So, look, this is your first function, the 6xy. We're going to treat that like our first function, and we're going to treat the z like our second function. So the product rule is the derivative of the first, so that's 6y. Remember, we're differentiating with respect to x. So that's the derivative of the first function times the second function, which is our z, plus the derivative of the second function. So derivative of z is 1 times the partial of z with respect to x times the first function. And then the derivative of 4 is 0, and derivative of 0 is 0. All right. Well, I don't know why I wrote the partial z with respect to x. That shouldn't be written there. All right, now we gotta solve this. All right, so you see the 3x squared and the 6yz. I'm gonna move those to the other side. So I've got partial z with respect to x. So look, this term and this term is getting moved over here. All right, and then this I'm going to factor out. So that's going to be times 3z squared plus 6xy equals negative 3x squared minus 6yz. And so I get partial z with respect to x is equal to negative 3x squared minus 6y squared. No, minus 6y z over 3z squared plus 6x plus 6xy. And then I'm going to factor out a negative. And then notice 3 goes into each of those. So that's x squared minus 2y z squared plus 2xy. And there's your partial with respect to x. All right, now let's take the partial with respect to y. So what I'm going to do here is I'm going to grab this equation and I'm going to pull it down here so we can see it. All right, so now the partial of z with respect to y. So this time x is a constant and z is a function of y. So the partial of x, the derivative of x cubed would be 0, and then that's going to be 3y squared plus 3z squared times the partial z with respect to y plus, and then once again, here you go, I've got product rule. So the derivative of the first function, that's going to be 6x, that's the derivative of the first, times the second function, which is z, plus the derivative of the second function, so that's partial z with respect to y, times the first 6xy. And then the derivative, the derivative of 4 is 0, derivative of 0 is 0. And then once again, this and this, I'm going to move over here. And then I'm going to factor out a partial of z with respect to y. So partial z with respect to y is times 3z squared plus 6xy is equal to negative 3y squared minus 6xz, and then divide both sides. So partial z with respect to y is equal to negative 3y squared minus 6xz over 3z squared plus 6xy. And then I'm going to factor out a negative again out of the top, and then 3 divides into each of those. So that's y squared minus 2xz, and that's going to be z squared plus 2xy. And there's your answer. All right. So that's a little implicit differentiation, defined implicitly as a function of x and y. Z is. All right, now what if we have functions of 3 or more variables? Okay, so you're going to have an x, y, and z. See how we have an x, y, and a z? This is a function divide. This is a function in terms of x, y, and z. It's 3 variables. And they want us to find fx, fy, and fz. Okay, notice in this one, it doesn't say z is defined implicitly as a function of x and y. This is a function in 3 variables. All right, so let's see what we got. This looks pretty easy. So we've got fx. So we're taking the partial of f with respect to x. So x is our variable. Everything else is constant. And so we've got e to the xy natural log z. So natural log z, that's a number. And the derivative of e to the xy is e to the xy times the derivative of the exponent. So what's the derivative of xy? Well, that's just y. Remember, y is our constant, x is our variable. And so this is your answer right here. That was easy. Now let's do the partial with respect to y. Well, that's e to the xy natural log z. Natural log z, once again, it's still just a constant. And then the derivative of e to the xy is e to the xy times the derivative of the exponent. What's the derivative of xy? Remember, x is a constant, y is our variable, so that's derivative of xy is x. And there's your answer. And then we've got the partial with respect to z. So this time, this e to the xy, that's just a constant. So that's e to the xy, and derivative of natural log z is just 1 over z. And so that's e to the xy over z. And there's your derivative. So that's pretty easy. So, you know, like I said, you've just got to be able to see that y is a constant if you're taking the partial with respect to x. X is a constant if you're taking the partial with respect to y. And if you have a function in 3 variables, if you're taking the partial with respect to z, x and y are constants. Partial of x, partial with respect to x, y and z are constants. Partial with respect to y, x and z are constants. Okay. All right, so now let's look at second partial derivatives. And here's some notation. So we got this partial fxx, fxx, f11, and then you've got these, you know, partial, the second partial of f with respect to x, or second partial z with respect to x. Mainly we'll be using this one or these two. Okay. And then we can do the partial of x with respect to y. So here's the notation. Mostly we'll use this and this. The partial of f with respect to y and then x, we'll be using this notation and those two mostly. And then the second partial of f with respect to y, we'll be using that, and that notation. Okay. So basically all we have here, this right here, so let's just look at this, the partial of x. partial with respect to x and then y. So mostly I'm probably going to use this notation, but you take the partial in this order. You take the partial of f with respect to x and then the partial of that with respect to y. But notice over here, if you're in this notation, you take the second partial of f with respect to x, and then with respect to y, you go this way, okay, this way. But when you're over here, notice that you're going this way as the order, the x and then the y. So I know it might seem backwards, but that's how you do it. Okay, so you take the partial of f with respect to x, and then you take the partial of this with respect to y. All right. So let's look at this. It says find the second partial derivatives. So basically what we're doing is we're finding all of these. Okay. And in order to find all of these, do you see we have to find the partial with respect to x and the partial with respect to y first? Okay, that's what we've got to find first. So let's do that. So I've got the partial with respect to x is 3x squared plus 2xy cubed, and then the derivative, that's 0 because y is a constant. And then over here, let's write the partial with respect to y is equal to, well, that's 0. And then that's going to be 3x squared y squared minus 4y. All right. So that's my partial with respect to x, partial with respect to y. All right. So now look how easy this is. So I've got the partial with respect to x and then with respect to x. So all this means is we start up here at the function, and this first one here, it tells us, okay, take the partial with respect to x, which I did here. And now this means I'm going to take the partial of this with respect to x. So that's going to be 6x plus 2y cubed. See, x is a constant. X is the variable. The 2y cubed is a constant. So we've got, see, 2y cubed x. This is a constant. So the derivative is just 2y cubed. All right, so there's that one. All right, now let's take the second partial with respect to y and then y. So what this tells me is I go to my function. So the first one here says take the partial of this with respect to y, and then this y tells me take the partial of this with respect to y. So that's going to be 6x squared y minus 4. And there's your derivative. And then let's do the partial x with respect to y. So it's just like you're starting at this first one right here and you're just following a trail. So I'm going to start at the function and I'm going to take the partial with respect to x, which is this right here. And then this tells me to take the partial of this with respect to y. So this would be 0 and this would be 6xy squared. And so there you have it. And then the partial of y, second partial of f with respect to y, and then x. So I start here, take the partial with respect to y, and then take the partial of this with respect to x. And so you can see that's going to be 6xy squared. And there's your answer. So it's really easy. You just follow what they give you. That's the way I look at it. Just follow what they give you. You go from here to here to here, or from here to here to here, or here to here to here. Just whatever they're wanting you to do. All right. So and you probably noticed that those are the same. So let's look at this. Clairaut's theorem. Suppose that f is defined on a disk D that contains the point AB. If the function fxy and fyx are both continuous on D, then the second partial with respect to x and then y, and the second partial with respect to y and then x evaluated at AB, they're equal. Okay. Partial derivatives of order 3 or higher can also be defined. For instance, the partial of x with respect to the partial of f with respect to x, y, and then y is equal to this. Okay, so it's just telling you the order that you're going to differentiate in: x with respect to x, then y again. Okay, and this is one way that you can do it. So it's the third partial with respect to x first, and then with respect to y, and then with respect to y again. And using Clairaut's theorem, it can be shown that all of those are equal if the functions are continuous. So it's what they're telling you there. Okay, you're just taking the third partial, so it'll work. All right, so here's one it's given us a nice little trail to follow here. So let's do that and see what we get. All right, so the first thing, we're going to take the partial with respect to x. So x is our variable. So the derivative of sine is cosine times the derivative of what you're taking the sine of. So the derivative of 3x is 3. Remember, x is our variable. Everything else is a constant. So the derivative of this is 0. And then we go to fxx. So we took the partial of this with respect to x and got this, and now we take the partial of this with respect to x, and the derivative of cosine is negative sine, so that's negative 3 sine 3x plus yz times 3, right? So the derivative of cosine is negative sine, so that's negative 3 sine, and then times the derivative of what you're taking the cosine of, which is 3. And so this is going to give us negative 9. Well, I'll tell you what, let's write it down here. So fxx is equal to negative 9 sine 3x plus yz. And then they're wanting us to take the partial with respect to x, and then we got to go to the y. So now we're taking the partial with respect to y of this one. So that's going to be negative 9 cosine 3x plus yz times what? Times the derivative of what you're taking the sine of. So remember, y is the variable, the x and the z are constants, so the derivative of 3x is 0, derivative of yz is z. And so now let's move, well, we'll see if we have enough room. So we got fxxy is equal to negative 9z cosine 3x plus yz. All right, but remember, we want to find that. So now we got to do the partial. I'll tell you what, let's do this. I think I might need enough room for one more line. So let's move that up just a little bit. All right, so now we take the partial of this with respect to z. So you're just following down. So notice here we've got to use the product rule. So we'll treat this as our first function and treat this as our second function. So the product rule is the derivative of the first, negative 9 cosine 3x plus yz plus what? The derivative of the second function. So that's negative sine 3x plus yz times the derivative of what you're taking the cosine of. So that's times y, right? Because z is our variable, everything else is a constant. So derivative of 3x is 0, and derivative of this is just y. and then that's going to be times negative 9z. And so now we got f x x y z is, what is that, negative 9 cosine 3x plus yz plus 9 yz times sine 3x plus yz. And this is the final answer that they want. All right, so that one took some work, but hopefully it gives you the idea of what's going on. Okay. All right, so partial derivatives comes up a lot in partial differential equations. So if we look at partial differential equation, and they give this, all this is just saying, okay, here's the solution to this, and just show that it's a function. Just show that it's a solution. Okay, show that this function is a solution to the Laplace's equation. So basically, we got to take the second partial with respect to x and the second partial of this with respect to y, add them together and show that it equals 0. All right, so we've got uxy is equal to e to the x sine y. So I'm just going to write that down again. Write the function down. So I've got the first partial with respect to x is just e to the x sine y. And then the second partial, so I'm taking the partial of this with respect to x, is just e to the x sine y. Remember, derivative e to the x is just e to the x. And then I've got the partial with respect to y. Well, that's just going to be e to the x cosine y. Derivative sine is cosine. And then the second partial would be, well, derivative cosine is negative sine, so that's negative e to the x sine y. Okay. Remember in this case, x is your constant, y is your variable. And so now if we take uxx plus uyy, that is equal to e to the x sine y plus this, which there's a minus there, so minus e to the x sine y, and that gives us 0. And that's all they're wanting to do. So basically they're just saying, here's some more practice of finding partial derivatives. And then last one here, verify that this function satisfies the wave equation. This is the wave equation. So we've got uxt is equal to sine x minus at. All right, so we're going to take the partial with respect to, let's do it with respect to x first, why not? So the derivative of sine is cosine x minus at times the derivative, remember derivative of sine is cosine times the derivative of what you're taking the sine of. But remember in this case, x is our variable, everything else is a constant. So the derivative of x is 1, derivative of at is just 0. And then we take the second partial. Well, the derivative of cosine is negative sine times the derivative of what you're taking the cosine of. So derivative of x minus at is just 1. All right, and then we've got the partial with respect to t. So derivative of sine is cosine times the derivative of what you're taking the sine of. So derivative of x minus at, this time t is our variable, so the derivative of x is 0, and derivative of minus at is just negative a. Okay. All right, and then we've got the second partial with respect to t. Well, derivative of cosine is negative sine, so the negative and negative, that's going to make it positive sine x minus at times the derivative of what you're taking the cosine of, which is negative a. So here we get negative a squared sine x minus a t. All right. And then we want to just take each of these and plug it into this. So let's plug this, replace this with this. So that's negative a squared sine x minus a t equals a squared times the second partial with respect to x. So that's negative sine x minus a t, and obviously you can see that they're the same. And then negative and a positive, that's negative a squared sine x minus a t. And there we showed that they're the same. All right, so that was kind of a long video, but hopefully you learned something from it. But I do hope you enjoyed this video. Check out my other videos. Give me a like, share, subscribe, comment, and I will see y'all in the next one. Later.